We're going to resume the chapter by starting with the kinetic energy theorem. Let's start by a small example. Consider a box that is placed on a horizontal support where we neglect friction. The box leaves from point A without speed and reaches point B with a certain speed under the action of force F. Then, when moving from A to B, the box's kinetic energy will increase. This increase is due to the work of the force F. And because the work is a form of energy, we can say that the variation in the kinetic energy of the box as it moves from A to B is equal to the work of the force F when its point of application moves from point A to point B. If we want to list the forces acting on the box, we know that we have the weight of the box, mg, and the normal reaction of the support, Rn. Note that Rn and mg do not affect the motion of the box, so we can add the work of Rn and that of mg between A and B, since their work is zero because their directions are perpendicular to the displacement. Then we say that the variation in the kinetic energy of the box between A and B is equal to the sum of the work of the forces acting on the box between A and B. This is the kinetic energy theorem. The kinetic energy theorem states that the variation in the kinetic energy of a system between two given instants is equal to the sum of the works of the forces acting on the system between the same instants. Now we're going to solve an application. Consider a box that slides on a very smooth horizontal support. We don't have friction at all. The box starts from rest at point A and reaches point B with a certain speed to be determined. The distance between A and B is 10 meters, for example. The mass of the box is 5 kilograms, and the force exerted on the box has a magnitude of 20 newtons. We're going to find the speed of the box when it reaches B by using the kinetic energy theorem. First step. We have to specify the system that we're studying. The system is the box. The second step. We have to list the forces acting on the system. So what are the forces acting on our system, which is the box? Friction is negligible. So we have the weight, mg, and the normal reaction of the support, Rn. And of course, we have the force F. So the forces acting on the system are mg, which stands for the weight of the box, Rn, which is the normal reaction of the support, and F, which is the force of traction that moves the box. In the third step, we apply the kinetic energy theorem. According to the kinetic energy theorem, the variation in the kinetic energy of the box between A and B is equal to the sum of the work of the forces acting on the box between A and B. So how do we find the variation in the kinetic energy between A and B? It is the difference between the kinetic energy of the final state and the kinetic energy of the initial state. So we have Ke final, which is Ke at B, minus Ke of the box in the initial state, which is at A. This is equal to the work of force F from A to B plus the work of mg from A to B plus the work of Rn from A to B. But we know that the weight mg is perpendicular to the displacement, and so is Rn. Then the work of each of these two forces is 0. Now the box starts from rest at point A. The speed at A is 0, so there's no kinetic energy at point A, because the kinetic energy depends on the speed. The kinetic energy at B, this is equal to half m VB squared. Since in this exercise the box is considered to be as a solid in translation, so we use half mv squared and not half I theta prime squared. We have the mass 10 kilograms. We have to find the speed at point B. Now the work of force F from A to B is found by using the work of a constant force. So the work of force F from A to B is equal to F times AB times cosine of the angle between F and AB. This is equal to 20 times 10 times cosine of the angle between F and the displacement vector AB. The displacement vector is to the right, and F has the same direction. The angle between these two vectors is equal to 0. So the answer is 200 joules. Hence, the kinetic energy at B is equal to 200 joules. But the kinetic energy is equal to half mv squared. So Ke at B, which is equal to half mv squared. This is the kinetic energy, and this is the speed Vv to be determined. Then Vb is equal to 2 Ke over m under the radical. This is equal to 2 times 200 over 5 under the radical, and the answer is approximately 8.9 meters per second. Let's solve another application. We have a box that slides down an inclined plane, and the inclined plane makes an angle of 30 degrees with the horizontal. The box is under the action of three forces: the weight of the box of mass 1 kilograms, the reaction of the support, and the force of friction of constant magnitude 3 newtons. The box leaves point A with a speed of 2 meters per second and reaches B with a speed of 3 meters per second. We want to find the distance between points A and B by applying the kinetic energy theorem. The system that we're studying is the box, that is a solid in translation. Then its kinetic energy is given by half mv squared. The forces acting on the box are drawn in front of us. So we can directly apply the kinetic energy theorem between A and B. The variation in the kinetic energy of the box between points A and B is equal to the sum of the works of the forces acting on the box between points A and B. The final kinetic energy, which is the kinetic energy at point B, minus the initial kinetic energy, which is the kinetic energy of point A, is equal to the work of Rn from A to B, plus the work of mg from A to B, plus the work of the friction from A to B. What is the kinetic energy at B equal to? Half m vb squared minus half mv a squared. What about the work of the reaction of the support? It is 0, since Rn is perpendicular to AB. Now the work of mg, this is equal to mg times AB times cosine of the angle between mg and AB, plus f times AB times cosine of the angle between f and AB. This is equal to half times 1 times 3 squared minus half times 1 times 2 squared. This is equal to 1 times 10 times AB cosine. Now, what is the angle between MG and AB? MG is vertically downward. AB is oblique in this direction. The displacement vector is in this direction. Now, what is the angle between the displacement and MG? Here it is. To find this angle, we do some calculation. We have 30 degrees, 90 degrees, and this becomes 60 degrees. Plus 3 times AB times cosine. AB is in this direction. F, the friction, is opposite to it. The angle between these two vectors is 180 degrees. The answer here is 4.5 minus 2. Cosine 60 is half. So 5AB. Cosine 180 is minus 1. Minus 3AB. And this is equal to 2AB. 2.5 equals to 2AB. So AB is equal to 2.5 over 2. And the answer is 1.25 meters. The distance AB is 1.25 meters.